Hi, my name is Joseph Ratmus and I'm doing Lag 5 presentation for the course of Physics 22212, Magnetic Braking with Faraday. So in this lab I will collect observational data of a magnet falling through a conductive tube of aluminum foil, model the magnet/tube interaction computationally, and compare my computational predictions with my observed data. So the key concept is the magnetic field of the dipole. Lenz's law, which is the current induced in a circuit due to a change in the magnetic field, is directed to the opposite change in flux and to exert a magnetic force which opposes the motion, Faraday's laws, and the magnetic force on a wire. So the materials for the experiment will be a smartphone, a bar magnet, a roll of aluminum foil which will be at least 1 centimeter thick, a metal stick or ruler for measuring the dimensions of the tube. So the procedure is that we're going to mark the knee pole of the bar magnet using magnetometer app, hold the tube vertically and position at the magnet just above the top opening. Record the magnet entering the top of the tube and leaving the bottom on the video. Find the time code when the magnet enters the tube and the time code when the magnet exits the tube. Calculate the time it took the magnet to fall through the length of the tube and repeat the experiment 5 times and calculate the average time. So here in Excel, I took the average of the 5 measurements and I got the time 1.164 seconds. And so the magnet falls down more slowly while inside the aluminum foil than falling in free space. I actually measured also when it hits during the free space, and it's actually like less than half a second. So here I have my glow script code using the computational method. We have our constants, our graph analyzation, the creation of the tube of aluminum foil, the numerical parameters, and the creation of the tube of aluminum foil, and also the creation of the bar magnet, visualizing the bar magnet, the initial conditions, the calculation of the magnetic field of the bar magnet, the calculation of the magnetic flux, and we also have the simulation loop, the gravitational force on the magnet, the calculation of it, also the calculation of the magnetic force from the tube of the magnet, and the calculation of the current in the ring. We also have the final steps, which is the computation of the typical B field at its ring, the calculation of the magnetic force on the magnet, and the net force on the magnet, and the update of the magnet's velocity and position. So here we have the visualization, as we can see with both the graph of the velocity and time. The red spot is the magnet who has fallen down, and we see that the computed time is 0.844 seconds, which kind of differs from the measured average time, which is 1.164 seconds. And I'm pretty sure that it's due to experimental errors. It's definitely my fault. And in interpreting the simulation, we see that the blue line is the induced current, and it has the counterclockwise current, and the red line is the clockwise current because of the induced B field of loop points, which is in opposite directions of change of the magnetic flux. If we flip around the magnet, the direction of the current is also flipped, but the velocity and the position of the magnet remains the same. And the same with the velocity versus time plot. When the negative slope, when they have this negative slope, signifies that the net force equals the gravitational force on the magnet only. But when the slope is 0, it signifies that the net force is 0 because of the electromagnetic induction slowing down, counteracting with the gravitational force, which is of the opposite direction. And what if the resistivity of the conductor were reduced as close as possible to 0? How the dynamics of the falling magnet change? So we can see from the formula that when because of the r is in the denominator, the I will increase to infinity. And we see also the force of the magnet will also increase, making the magnet will take longer to fall. And if we have holes or slots or cut into the tube, how will this affect the ring currents of the model? The magnet will fall faster because there will be less ring current/materials to make the magnet slow down, and therefore the induced current will be less. Thank you very much.